A district health authority comes to your team with a critical problem. Emergency response times are lagging, and they need to know exactly where to build a new ambulance station to fix the issue. Faced with this, a beginner immediately focuses on the tools, asking, which GIS software should I open and where do I download the data? But a spatial thinker pauses. They ask, how do I decompose this into smaller questions? By the end of this module, you will know how to take a vague, high-stakes request like this one and break it down into a precise, step-by-step analytical plan. To do that, we have to establish one absolute rule. You must resist the urge to map anything right away. The software tool you use is the very last decision you will make. Opening a program and loading data without a structured plan often leads to analyzing everything while answering nothing specific. It creates a high risk of answering the wrong question entirely. Step 1 is recognizing that where to place a station is actually 4 separate sequential sub-questions. We have to start by finding out exactly where the current system is failing. This map illustrates our first sub-question. Where are the response time gaps exceeding 12 minutes? The existing station is our center point. The green zone represents areas within an 8-minute drive. Yellow extends to 12, and that red zone on the edge is our gap. We find that gap using network analysis. We aren't measuring a straight line across the map. We are calculating actual drive times on real roads, using speed limits and traffic patterns to define exactly who is waiting too long. Now that we see the physical gap, we have to determine if it is actually a problem by locating where the emergency calls are originating. A coverage gap over empty farmland requires a very different response than a gap over a dense residential neighborhood. This map updates to answer our second sub-question. Within the gap, where is the highest demand? By overlaying historical call records, we perform pattern analysis. The densest cluster of orange circles inside that dashed border isolates our true priority search area. You cannot look at real estate until you have defined where the coverage fails and validated that actual emergencies are happening in those zones. With our priority zone defined, our third sub-question asks, which specific sites inside this boundary can physically house an ambulance station? We filter this grid of land parcels using suitability analysis. We apply strict physical criteria. The land must be zoned for public use, have a minimum of 500 square meters, sit outside flood zones, and have major road access. 20 parcels go in, and only 3 viable candidates come out. This diagram shows the results of our fourth sub-question. If we build a station at one of these sites, how does the district-wide coverage change? Candidate A improves coverage, but only partially. Candidate C has good numbers, but shifts the remaining gap to the east side of the district. We use scenario modeling here to compare the mathematical outcomes. Candidate B yields 91% total coverage and reduces the average gap by 14 minutes. It earns the recommendation because it provides the most balanced improvement for the entire district. The sequence of these steps is non-negotiable. You cannot accurately select a parcel or test a scenario without first defining the coverage gap and the emergency demand. The answers to our 4 sequential sub-questions map perfectly onto the 5W framework. By following this order, we have turned a vague request into a precise blueprint ready for execution. This completed grid is your actual project deliverable. It provides a precise plan that any analyst or any AI system can execute with confidence. Before we proceed, we validate this plan by testing it against 3 common mistakes that often ruin spatial analysis projects. The first mistake is jumping to how before finishing what. Our plan shows we defined the 12-minute response threshold before we ever touched a software tool to map it. The second mistake is forgetting the why. Mapping response times is just an activity. Our why specifies an actionable purpose, reducing average response time to inform this year's budget allocation. The third mistake is working at the wrong resolution. Our plan correctly shifts from a broad neighborhood-level analysis for finding the gaps down to a highly specific parcel-level analysis for selecting the site. Completing this grid acts as a safeguard. It helps protect the project against common pitfalls like wasted time, aimless mapping, and misaligned data scaling before the technical work begins. Look closely at what we just accomplished. We have not opened any software. We have not downloaded any data. We have not written a single line of code to solve this complex problem. The most critical phase of spatial analysis happens entirely in your mind, before you touch any technological tool. You now possess a repeatable, structured system to convert any vague request into an actionable execution plan. In the next module, I am going to show you something that surprises most people: how changing the framing questions can make the exact same dataset yield completely different, yet equally valid answers. Because ultimately, the quality of your analytical question dictates the value of your spatial answer. Next, I will show you how taking the same dataset but changing your framing questions can completely alter the reality your map presents.